We've now created our optical system geometry. We have created and inserted an LED, and we've traced rays. We're now ready to analyze our system, which is the fourth and final step in the Apex workflow. We've added a detector to our system, and we can see that the detector doesn't capture all of the rays in our system, but we get enough to give us a sense of the performance of our faceted reflector. Under the Analyze tab in our Command Manager, we can see that we have a number of options available to us, including the ability to select subsets of rays from our full ray trace. We can print statistics on position or direction of the ray set, and we can also immediately calculate irradiance, intensity, or radiance for the entire system or subsets of parts and or surfaces within the system. In this case, we'll do an irradiance plot, and we're going to select the front of the detector surface, and we'll select the Selected Surfaces option under Geometry. We're going to print a 2D spots diagram, which is the locations of all ray intersections on the front of the detector surface, and we'll print a false color irradiance map. The geometry for our irradiance plot will be taken directly from the detector surface, but we can manually adjust the size of the plot if we wish, and we can also adjust the resolution and aspect ratio of the resulting plots. And we'll go back to our spots diagram, and in this case we can see that it appears that the bulk of the energy is contained within a ring about the central axis of the system. If we switch to our irradiance plot, we can see that our spots diagram does tell us the story that most of the energy or irradiance on the detector is contained within a central ring, and we can see the effects of statistical or shot noise on the resulting plot due to the limited number of rays that we've traced. Now we also notice in our Analyze tab that since we performed the irradiance, we now have a number of other options for plotting that are available to us, including the ability to create a contour plot, a picture plot, which is shown here, isometric, mesh, or distribution, or in other words, a cross-sectional view of the irradiance. We'll create a contour plot, and we can see that we get a nice 3D view of the irradiance map on our detector surface. Now, one of the nice things about the ray trace is that we can immediately post-process the data, and in this case we'll create an average, but rather than a nearest neighbor average on our irradiance map, we're going to perform a radial average about the centroid of the distribution. And we can again immediately create a contour plot. And this gives us a much better sense of the irradiance on the detector surface by taking this radial average. It also implies that we might not need to trace nearly as many rays for a symmetric system as we might for other systems. Now that we've viewed the irradiance distribution on our detector surface, we can immediately calculate the far field intensity, in this case for all rays in the system, including rays at the detector as well as rays coming from the faceted reflector which miss the detector surface. We'll again create a 2D spots diagram, in this case in direction cosine space, showing the angular distribution of our ray set, and we'll plot an intensity map in cosine space as well as in angle space. Now, the limits of our plot will initially be in direction cosine space, and we can again set the resolution and aspect ratio for the resulting plots. And we can see that these plots have been added to our Optics Manager. If we look at the spots direction plot, we can see that the bulk of the energy is contained about a central cone around the optic axis of the system. And this is confirmed in our intensity plot, here shown in direction cosine space. We've plotted the same distribution information in angle space, and we can again see that the bulk of the energy is contained in a central ring around the optic axis, but that we have a hole in the center. Now finally, we might choose to create a distribution section, which in this case gives us the option of creating a cross-sectional view of our far field intensity. And we'll create that far field view at the halfway point of our intensity plot. And we can see again in the cross-sectional view the central hole in the far field intensity. And we can see that the total angular distribution of our system is approximately plus or minus 35 degrees. Now, these are just a few of the types of analyses that can be performed in the fourth and final step of the Apex workflow.